Hello. Welcome to my first video. This is quite exciting, isn't it? Uh, in this one, I'm gonna just kind of go over a little project I've been working on recently. Uh, Multi-parametric Taylor polynomials. Basically, getting a Taylor polynomial to predict multiple different parametric equations at once. So you can see over here, we have a list of a few different parametric equations. Here's one parametric, here's two parametric, 3-parametric, 4-parametric, 5-parametric, which you can then see graphed in this little coordinate place over here in Desmos. And the idea is basically we have a sample point, and the closer the sample point is to one of these, the more the Taylor polynomial will form to that parametric equation. You can see, move it over to this sinusoid over there. Yeah, there you go. Right. And then we also have a list of centers over here that define the center of our Taylor polynomial for each of these parametrics. And the idea is that we can add or subtract as many of these as we want, as long as we keep this consistent, and it should hopefully just work. So let's get into the math behind some of this. Let's start out with the Taylor series, because as you can imagine, they are rather important for this. So let's just write down the definition of a Taylor series just out of the box, right? T of x equals the sum of the nth derivative of f evaluated at c divided by n factorial multiplied by x minus c to the n, right? That's just a standard out-of-the-box Taylor series. However, how are we actually going to apply this to a parametric? Well, let's get a little parametric, and we'll write out just like a standard parametric. f1 of t equals, and I'll move over here, there we go, f1x of t, f1y of t, right? Now what we can do is use a Taylor polynomial to predict the x component and the y component of this. So we can then write that f1 of t equals, and this is going to get a little bit big, but we're basically just inputting our definition for a Taylor series and applying it to the x and y components. So the sum of f and x, and that's the nth derivative of t divided by n factorial multiplied by t minus, oh, sorry, that should not be evaluated as t, that should be evaluated as c, t minus c to the n. That's our x component. Our y component is pretty much going to be the exact same thing, except we'll just use f1y instead of f1x. So the sum, the nth derivative of f1y, evaluated at c, divided by n factorial, multiplied by t minus c to the n. And there you have it. We've used a Taylor polynomial to predict a parametric equation. However, in our example, we don't want to predict just one parametric equation. We want to predict as many parametric equations as we want and then blend in between them. So a good way to start would be to then define a sequence of parametric equations, as so. So we have fn of t equals, then we'll have that f1x of t, f1y of t, and then, as you might imagine, f2x of t, f2y of t, all the way off into the distance of f, oh, that should be a parenthesis there, fnx of t, fny of t. I'm going to rewrite that f because it kind of looks like a p at the moment. Ooh, that's an even worse f. Hang on. There we go. That's at least readable as an f. Right? So that is a sequence of parametric equations defined as f and t, where f1 of t represents this parametric equation, f2 of t represents this parametric equation, fn of t would represent the nth parametric equation. Now you'll also notice for Taylor polynomials, we need a center. You can see that center being used there and there, right? So let's define another sequence of centers. We can call this C of n. And we'll set that equal to C1, C2, all the way off to Cn. So C1 represents the center for a Taylor polynomial which is predicting f1 of t. C2 represents the center for a Taylor polynomial predicting f2 of t, and so on until we get to Cn. So now what we can do is create a sequence of parametric Taylor polynomials to then predict each of these parametrics in here using this sequence as our center. And we can call this Tn of lowercase t. And I'm just going to write out the nth term for this, because writing out the first term, and then the second term, then the nth term would make this go on for very long. So, and I'm also probably going to move that down so that we have a little bit more space here, just down there. So, and this is just going to be using the definition of our Taylor polynomial, or Taylor series, which we defined up there. Good thing that we wrote that down, yeah? So, sum, and I'm going to use k here because we're already using n for the index of the sequence. So, k equals 0, it goes over to infinity, of f n x, that's the kth derivative. Is kth a word? I think kth is a word. I'm going to pretend like kth is a word for now. So that's the kth derivative of fnx, evaluated at Cn, divided by k factorial t minus Cn to the power of k. And then we can do basically the exact same thing for the y, except using fny. So we have the sum k equals 0, infinity, f n y, that's the kth derivative of that, evaluated at Cn, our center point, divided by k factorial, multiplied by t minus Cn to the power of k. And there you go. That is a sequence of parametric Taylor polynomials, right, predicting each of these parametrics. So, for example, t1 of t would use the center C1 to predict the parametric F1 of t, right? And you can see these indices are really, really important because they all have to align, hence the ordered nature of sequences. However, we have a list of Taylor polynomials, but in our example, we just had one equation that kind of blended between all these different Taylor polynomials based on a point's distance to the different functions. So let's define that point. We'll call that point P for now. We'll set that equal to Px, Py, just the two coordinates of it, right? And now we can calculate the distance between P and our parametric equations up there just by using the distance formula. We'll use dn of t, yeah, we'll use t, equals square root of px minus fn x of t, that's squared, plus py minus fny of t, that's squared, and the square root of that whole thing. And that will get us the distances between p right here and our parametrics. So let's visualize that, shall we? Let's make a little coordinate plane right there, just like that. And let's say we have a little parametric that kind of looks something like that, right? And we'll call this f1 of t. And let's say then we have our point right about there. We'll call that p, right? Well, let's say that point is t equals 1. So to attain that point, we could just evaluate f1 of 1, right? Well, that means that d1 of 1 equals this distance right here, right? So we can label this d1 of 1. Gives us that distance. So now let's look at when t equals 2. Well, let's say t equals 2 is somewhere right around there, right? And again, this is just an example. I'm just kind of assigning values so we can see these mechanisms working. So let's say t equals 2, so we can attain that point by calculating f1 of 2, right? Well, the distance here can be attained via d1 of 2, right? So I'm going to make a little arrow pointing right there. Let's say we have then a final point right here or so, and that is t equals 3. So that point can be attained by evaluating f1 of 3, right? And this distance right here will be given by d1 of 3. So now let's visualize what d1 would look like. So I'll make another coordinate plane over here. Get a lot of coordinate planes in. Well, actually, it's just 2. I guess that's not a massive amount. Oh, and actually, before we do this, let's just assign some values to what these could be. So let's say that this distance equals 2. Let's say this distance equals 1. This distance maybe equals 1.5, right? So this distance right here would be 2. This distance right here would be 1. This distance right here would be about 1.5. Now we can visualize this. Let's say d1 right there, and we know that equals 2, so 1, 2. d1 would be right around there. Now we can then visualize d2. So d2 is equal to 1, or d1 of 2, sorry. So d1 of 2 is equal to 1, so right around there. And d1 of 3 equals 1.5, so right around there or so, right? So D would look something kind of like this. Now, we ideally want to then find the minimum distance between the point and the line. So, for example, if we're right on top of the line, that minimum distance would be 0. If we're a little bit farther out, it would be like a low number. If we're very far out, it would be a much higher number. But the point is that it would just be one number, and it's the minimum value of D per parametric equation. So what you could do to find this is a little bit of minimization, use a little bit of calculus. However, we run into a little bit of a blockade with that. because we don't actually know the value of fn x or fn y. We don't actually know the equations behind that. So if we started down that minimization path and we did something like d 1 prime of t and find when that equals 0 to find critical points and then minimize, well, we could definitely find this derivative, but we couldn't actually find the t value that makes it equal to 0 because we don't know what these are defined as. So to get around this, I'm going to cheat a little bit in the sake of preserving generality and have mn equal the minimum of dn of t, right? I know it's a little bit cheating, and we'll go over how that is then implemented into Desmos. And if you knew the values of these, so if you had a certain situation and you were applying them, or applying this concept to certain functions, then you could totally use minimization to find this. It's just that when developing the concept, we want to try and keep this as general as possible, right? So that's why I'm just writing this, just kind of like a little shorthand, right? Well, ideally, we'd have some equation that then takes these minimum values and interpolates between different Taylor polynomials, or parametric Taylor polynomials, based on that minimum distance. There's a lovely little equation for this that I'm going to call capital I. That's going to be I of n, because again, this is going to be a sequence. I'm going to set that equal to 1 over mn, oh, that's mn, divided by the sum. I'm going to use k here again to remove confusion. 1 over mk. There you go. So let's look at how this actually works with a little example, right? So let's say we have I1, and that would equal 1 over m1. That divided by, let's say we have three different parametric equations. So that would be 1 over m1 plus 1 over m2 plus 1 over m3. So this is the minimum distance between the point and our first parametric equation. This is the minimum distance between our point and the second parametric equation. And this is the minimum distance between our point and the third parametric equation. So you can see, as m1 gets less and less and less, this numerator will get bigger and bigger and bigger. And scaling with it will be this first term of the denominator. So those will get super, 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 super big, shooting off to infinity, while these will generally just kind of stay finite values. So as these go shooting off to infinity, leaving 1 over m2 and 1 over m3 in its dust, these become insignificantly small, because when compared to infinity, pretty much everything is insignificantly small, giving us something close to 1 over m1 divided by 1 over m1, which is about 1 when we're right on top of the line, right? Now, what's also pretty interesting is, let's say we are right on top of m1, and we're looking at, so m1 kind of equals 0 in this case, because we are on top of the line. Now, say we're right on top of m1 and we're looking at I2. Well, I2 would equal 1 over m2 divided by 1 over m1 plus 1 over m2 plus 1 over m3. Well, if m2 doesn't equal 0, right, or isn't rapidly approaching 0, this is going to be some finite number. However, we know that m1 does equal 0, or at least is very, very close to 0, meaning this bit is going to go shooting off to infinity. Now, if this is going shooting off to infinity, these other terms again become pretty insignificant, because it's just infinity plus some numbers, which is still kind of infinity. So then that is then going on over to 1 over m2 divided by infinity, which is just kind of going to 0. We could more rigorously prove this with limits if we wanted, but I'm just doing this for the sake of understanding. Yeah, so you can see, as we are right on top of m1, I1 is going to go to 1, and everything else, I2, I3, etc., is going to go down to 0. So it's kind of a nice low interpolation equation that goes between 0 and 1. Now, we can then multiply this by these Taylor polynomials to interpolate between different Taylor polynomials. So what that might look like is something a little bit like I1 times T1 of T plus I2 times T2 of T plus I3 times T3 of T all the way off into the distance of I n times T n of T. Now you might notice that this looks like a perfect opportunity for a summation. And you'd be right, we can totally use a summation for this. So let's simplify this down a little bit with oh, that's a terrible summation. My hand slipped at the last minute. Simplify it down a little bit with a summation. So this is just I n times T n of T. And that is our final equation. So now let's head back to our simulation so we can see some of this mathematics in Desmos. So you can see our list of parametric equations up here and our list of centers. This is our list of Taylor polynomials. This is a third degree Taylor polynomial, so there's that. And then I know I mentioned a little bit that the minimization of our distance function is a little weird in Desmos, so I'll get into how that works. So under minimization, you can see actually our distance function graphed right here. You can see that's all those purple lines. So for example, as we get close to this parabola, you can see this represents the distance of the parabola. As we get like right on top of it, it starts to get pretty close to 0 at one point. As we come close to the circle, you can see some of these get pretty close to 0, right? And remember this relates to the t value. So close to here, that one gets kind of close to 0, right? As we get close to this line, that one starts touching on 0, right? So you can see this is the distance between the point and the line. Now, the minimization of this gets a little bit weird because I found that Desmos can't actually minimize functions. You can't just say like min this function. So instead, what I've done in Desmos is basically created a whole ton of points along our distance function. So you can see if I graph this distance function over top of it, you can see the points align with our distance function. Now, the density of points and how far they extend is controllable under variables, right here and here. And then what Desmos can do is find the minimum value of a list. So we can actually minimize the y values of these points to find the kind of pseudo minimum of our distance. It's not going to be perfectly exact, but for most intents and purposes, it's going to be pretty much spot on, right? And that's how we do the minimization in Desmos. It's a little bit weird. Ideally, we'd use the calculus method, but as I said earlier, you can't really do that without losing generality. So if we look at the different pieces, you can actually see a lot of the different equations that we played around with here. For example, under visualizations, yes, this is our final equation. You can see this is our interpolation, right? Except inside of the example I used m right there. Inside of this one I used dm for distance minimum. That was our final equation. You can see, as I pointed out here, this is our Taylor polynomial, which was also defined. You probably recognize these. And altogether, we can see this simulation, which is pretty cool. So I will post the simulation inside the description so you can play around with it. Especially it adds a little bit of context to a lot of the mathematics that we've already done. And I do hope you enjoy. So fingers crossed I'll see you guys next time, and goodbye.